So let's get going. Let's see. Okay, so here's my little concept map. Where are we? So we're in the second part of how we organize hardware with compute models. And I'm going to give you readings for next week, which is starting to move on to the next sort of subtopic, which is how do FPGAs compare against other compute devices, which we talked about a bit about in Lecture 1. But we'll try to get a few actual numeric bounds. But that's the readings for next week, start moving towards that. Today we're going to keep talking about compute models. Okay, so some administration. So 2 papers for next week. Again, you only have to submit 10 summaries. So if you go, that's 2 papers is too much, then I would read this one. I'd say this is the more important of the 2 papers. This paper, the part that's really interesting about this paper to me is that it tries to very rigorously check what is the cost of having a processor. So how efficient is it to make specific streaming hardware to compute something versus using a processor? And they actually implement both systems on an FPGA. So it's not trying to say how efficient a hard processor is. It's basically trying to say for the compute model of a processor where you have instructions and they tell you what to do, how efficient is that versus building hardware that just does what you want. They're both built in an FPGA, so all the kind of programmability of overhead of an FPGA is common to both. So I like this paper because it's one of the few or maybe the only paper I know that tries to sort of rigorously separate that out. What does it cost for us to be able to be programmable in a processor style way? Second one, not as important, but gives like another way to get quick bounds on what kind of compute device you might want to use. It basically goes and gets like upper bounds, essentially. Like how many resources, how much computation could we possibly get in this device, how much memory traffic, how much other I/O traffic. It's a kind of a simpler way to study things, not always accurate, but gives some insights. Okay, other administration. So assignment 1's released. It took me a few days to every year work through all licensing issues. So if you use the UG machines and the versions I pointed you at, you shouldn't have any licensing issues. You can use other versions of Cordis, do it on your own machine, whatever you want, but you might have licensing issues. The licensing is kind of a pain for CAD tools. So we're 13% of your final marks due October 8th. Again, it's not, it's intended to be partially tutorial. You know, how do you use these CAD tools and then try some different compute models and some pipeline optimizations. We're going to have our first class test. We'll have 2, so this will be 1 of 2. On October 21st, at the start of the lecture, it'll cover the, that's interesting, I didn't manage to save this properly. It'll cover the lectures up to that point. So there'll be the first 6 lectures and the readings that go with them. I'll focus more on the lectures than the readings, but you should actually do the readings too. It's closed book, right? So those are the other 2 things I had written here that'll be on Quarkus, but somehow didn't show up on the synced slides. I'm not intending to make it super long. I'll give you enough time that you're not rushed, or super tricky. So just basically pay attention in lecture, do the readings, but I'm not going to try to ask you like, here's some incredibly subtle question that was on page 16 of some reading. Okay, so try not to get super worried about that. Just pay attention to what's going on in class. It checks that. Any questions on any of the administrative stuff? Yeah.
Just like back to the 2 papers for next week.
Yeah.
There's like a questionnaire for each paper, basically.
There's a questionnaire for each paper, but because you only have to submit 10 questionnaires, if you just go, I can't take it, I can't write a questionnaire on both these, then don't do it. Although usually people get more busy towards the end of the semester, so it's not a bad idea to get ahead of the game, in my opinion. And if you do more than 10, I'll take the best 10 marks, and I'll also kind of give you extra credit if I see you're a keener and you did all the readings. Yeah?
If we don't read the second paper, will it affect on the test?
No, so that's a good question. Okay, so I won't put anything on the test that comes off of this, okay, that I don't talk about in lecture, okay? So I should be more organized on this. So yeah, let's consider this one optional, right? If you're too busy, then don't read it, don't do a questionnaire on it. I'll tell you the highlights in the lecture, that'll be enough, okay? Probably what I tell you in lecture on this one is enough too, but I like it more, right? I think this is a good one. It's not that this is a bad paper, but I just find that this is actually, I think it's sort of a fundamental question. And this is, as I said, one of the few papers that I've seen try to answer this. Of what is it really costing us to solve something with a processor instead of making specific hardware? So I'd really like you to read that one, okay? Yeah, it's a good question. Maybe what I'll do, I'm going to, on Quarkus, when I post these, I'll put like an optional beside things where I will promise I don't ask a question that on a test that would come from that paper. Okay, so then you can, you can, without fear, not read that paper. I think maybe I'm doing a bad thing pedagogically by doing that, but I understand the questions. So, okay, so let me turn off the projector and I'm going to use the chalkboard for a while. So there are, this was at the front of the lecture, at the front desk. Has anybody lost their earpods or sunglasses? Okay. Alex, yeah, I thought you were looking less cool than usual, so I didn't want to say anything, but maybe it's your sunglasses and your earpods. So, okay, so we were talking about compute models and optimizations that we could do. So, basically, streaming data flow models. We talked about you can make an inelastic pipeline, which is basic pipeline registers. If you can't, if there's some imbalances in latency, you can't quite tell how long operations will take, then you can make your pipeline work and absorb some of those latency imbalances if you put buffering in, put valid signals on your data, and put back pressure signals to stall. And that becomes what's called an elastic pipeline. Okay, and then we talked about how you could apply certain optimization techniques kind of mechanically. So for example, if you have an inelastic pipeline, you could draw these cut lines and decide I can put more pipeline registers in and I can make it run faster. So that was one optimization we talked about. Another optimization we talked about was that you could, if you had a piece of hardware that was faster than you needed, you could multi-thread it, so send multiple streams through. And the kind of rigorous way to do this is actually embed a tag, an ID inside of your data stream so you can take apart the data properly on the other side. Okay, so those were kind of different ways we could optimize streaming hardware. So let's talk about one more. Okay, so time domain multiplexing loops. And let's see. I think I lost some of my lights. Let's try that. Okay. Okay, so loops were a problem, right? When we had a loop, we couldn't just go and pipeline it because it changed its function. Changed its function because we were changing the latency around the loop, and that was fundamentally changing its functionality. Or if we thought about it as we have to do a cut, we couldn't find a cut that disconnected inputs from outputs. There was like no directed output, no directed cut that cleanly separated things. So we couldn't pipeline it. So that's a pain. And it means in deeply pipelined circuits, loops often become our limiting path, and they're harder to fix. So, but there is at least one thing we can do to them mechanically. So let's look at an example. So say I've got F1 and it goes to F2. This is the same example I showed you before. We register that, okay? And we come back around. Okay, so there is feedback. And we had a sequence of data going in, X of I, and we had a sequence of data coming out, Y of I. And we concluded last week that if we stuck pipeline registers anywhere in this loop, it would change the functionality. Okay, so as a designer, you might be able to rewrite this loop, but you need to actually go and think about it, right? Maybe you could rewrite it in a totally different way. So, and that's an optimization that humans do, but no CAD tool really knows how to do. There is something that you can do mechanically here. So I can't pipeline it, but what I can do is something, I can time domain multiplex it, okay? So I have one piece of hardware here, and what I can do is I can put more registers in. So let's say I put a register here, okay, which is going to shorten my, my critical path was going all the way around this loop. Now my critical path goes just halfway around the loop, right? Either that half or that half. And so I can clock it faster. But as I said last week, I changed the functionality, right? This is no longer producing an output that is a function of the, the current input and the previous output. It's now a function of the current input and the output that happened 2 cycles ago. So it's wrong. But I can make this work again by saying I'm going to time domain multiplex it. So what I do, let me erase this. Okay, so if I put this register in, I have to put another bit of circuitry in. So I can put in two streams of data. Let's call them x1 and x2. Okay, so those are two totally independent streams of data. Maybe it's a wireless system again. They're coming from two different antennas. And what this is now doing is basically every cycle, I'm going to flip between the two inputs. I'm going to take cycle 0. I'm going to take something from x1. Cycle 1, I'm going to take something from x2. Cycle 2, I'll go back to x1, and so on. So I'm going to ping pong back and forth between my two streams. Okay, so what does that do? It means that from the point of view of one stream, my output is still a function of the current input and the output value one cycle ago, right? Like previous output value for that stream. That's actually 2 clocks ago, but because I'm interleaving two streams, it is only one value earlier in my stream. Does that make sense? So the time domain multiplexing that I did here has enabled me to basically pipeline this more deeply. And I have to do both at the same time. If I basically want to do this time domain multiplexing and make it work, I need to put this register in. So, but the combination of the time domain multiplexing and putting this extra register in, which doubled the latency around my loop, they've effectively canceled out the impact on one stream. So now it still does the same thing for each stream. Okay, so basically at the output, I'm getting something like this. I'm getting y1 of 0. Then I get y2 of 0. So the first value for my other stream. Then I get y1 of 1. So the second value for my first stream, and so on. Okay, so I have this one. This is stream 1 here. And this is stream 2. And I've interleaved the values between those two. So I've time domain multiplexed them. If I write out the equation of what I'm getting, y1 of I is equal to f2 of f1 of the current input. Okay, so x1 of I. And it's whatever y value came out 2 clock cycles ago, because I put this register in. The y value that came out 2 clock cycles ago is y1 of I minus 1. Okay, if I go back in this stream 2 clock cycles, I get something from y1, but one cycle earlier in the, like one value earlier in the sequence. And that's half of my output. The other half of the cycles, I'm going to get y2. And it's the same function. Okay, so y2 is f1 of f, or f2 of f1. But now it's always a function of the second stream, x2 of I, and the second output stream, y2 of I minus 1. Okay, so hopefully that convinced you, right? I am getting the same sequence of values for each of these two streams. So this doesn't help me if I just have one stream of data that I want to process really fast, but it does help me if I've got a lot of parallelism. Like again, signal processing, this is fairly common. Maybe I've got multiple antennas, multiple channels, multiple customers, whatever, and I can basically run them through this hardware. Because I put this pipeline registers in, this hardware will run around twice as fast. You know, if this was a loop with a lot of logic on it, putting a pipeline register in will make it run nearly twice as fast. So this was pretty efficient. I put in 2 streams. I only get a value for each stream. You know, every second clock cycle, I get a value for stream 1, and then also a value for stream 2. But I can clock it about twice as fast. So each stream kind of goes through about the same speed as it used to go through, but now I get 2 of them. And I couldn't do this with just straightforward pipelining, because I would have changed the functionality. So does this make sense? Yeah.
So just as a general rule of thumb, the amount of registers you have on loop cache like this, you need to multiplex that many.
Yeah, so essentially this optimization starts from a design that works. Okay, so you wrote a finite state machine or something, and it works on one stream. So maybe it has 1 cycle of latency, that'd be pretty common, but maybe you wrote it with 2 cycles of latency. But whatever it has, if you want to time domain multiplex it, the mechanism, what you have to do is every register around the loop you have to make 2 copies of that register, and then you have to time domain multiplex by a factor of 2. Does that make sense? So it works for loops with longer latencies as well. So let me click on this. Let me do that again. I think that's off. Okay. So this is actually given a name. So this optimization is called C-slow retiming. All it means is pipeline more deeply and then retime to get the registers in the right spot. So it can be done mechanically. So what it is so this C is how many streams you're going to put through. Okay, so you start with hardware that works properly for 1 stream of data, and you want to put, for example, 2 streams of data. So that would be called 2-slow retiming. But I could do it for 3 streams or 4 streams or 5 streams as well. So that's the C. So what you do is you make C copies, and in our example, C was 2, of each register. Okay, and those copies are in series. Okay, so this is C equals 2. And you do that for every single register that is in your design that you're going to do this optimization on. So that's the first thing you do. The second thing you do is you now have to send in interleaved streams of data. Okay, so you send in C interleaved streams of data. So if I do this optimization, like if I did this here, I would have put my second register right there. And then I time domain multiplex by a factor of 2, and it will work. But clearly, I didn't get a lot of frequency benefit from this. I just put 2 registers back to back, so my critical path is pretty much the same. So so the name kind of tells you what to do. After you've done this optimization, you retime it. Okay, so you either use a CAD tool to retime it, or you can do it by hand, right? Because the rules for retiming are not that complicated. It's basically I could move this register back over this combinational logic, right? Move it from the output to the input. There was 1 output, there's 1 input, so I don't have to duplicate it or anything. It just goes back here. And that would be a legal retiming, okay? So you retime to distribute the registers. Okay, so when I put this up originally, I essentially did that in those 2 steps in 1 step. I actually put an extra register here, which is already in kind of the right spot. In a more complicated design, it might be hard to see that, right? If I have registers all over the place. So a mechanical procedure like this that says, well, okay, double them all, now go and retime them 1 by 1 it's a recipe, right? You can do it with less worries about breaking the circuit. Yeah?
I'm just slightly, not confused, but just the wording of the first step. So we already had a register to start.
Yeah.
And you just made an additional copy.
You made an additional copy. So I doubled the latency. That doubling of the latency is important in order for me to put in 2 streams and get the right behavior.
So is it, I guess in this case, is it we have C registers on the path, or is it just making C copies and you need 2 additional copies?
Yeah, for every single register you actually had in your design, so this was 1, you make C, well, you make, I guess, C minus 1 copies, right? Okay, so how do I write this? I see what you're saying. Make into C copies. C is the final answer. Does that make sense? You're right. So you don't make 2 copies of it and wind up with 3 unless you want, yeah, because you're right, that wouldn't work, right? So if I say C is 2, I need to wind up with 2 registers everywhere I used to have 1 register. Yeah?
Well, another way of fixing this, obviously it's not time domain multiplexing. Could I duplicate my loop for one for each stream?
You could do that, yeah.
And then just enable every other cycle.
Yeah, and that's another technique people could do. So let's say this was limiting the speed of my system. I got some data path that runs really fast, but I also need this, and it's got this annoying loop in it. you could make many copies of it, and then basically you could time domain multiplex between, well, you could basically if the rest of your hardware is faster, at the output of your 2 copies of this, you could basically multiplex them together in time and send them into your faster hardware. So you're right. Another way you can match this thing as too slow is make many copies of it. The nice thing about C-slow retiming is it's really relatively low cost, right? So let's say this is a lot of logic. I didn't duplicate all that logic. I just stuck another bank of registers in. And particularly in FPGAs, again, registers are pretty cheap because they've pre-built registers in many, many places. So until you get quite register rich, it's usually you don't even really notice much difference in terms of device utilization. There's a certain point at which it hurts, but yeah, it is more efficient than just duplicating the unit. Okay, so what's the gain of this? Assuming that these are reasonably big chunks of logic, this can be clocked approximately C times faster. Okay, so when we did too slow retiming, we would get a factor of almost 2 in clock frequency. So what that means is we get C streams of data at roughly what the original rate was. Okay, our output values for each stream are further apart in terms of clock cycles, but the clock cycles are shorter. So we kind of filled in dead time in a sense with other streams, and we got more efficiency. This eventually breaks down, right? Like if you go, I'm going to do C equals 1,000 retiming. I'll replace every register with 1,000 registers, retime it, and it's going to go from running at 100 megahertz to running at 100 gigahertz. Like that's not going to happen, right? Okay. So there's a certain point at which, yeah, these registers themselves have some intrinsic delay, and they've kind of pipelined everything, like every wire, every function, every LUT, every DSP block, and you no longer get anything for them. So, reasonable values are like 2 to 8 maybe, right? Depending on how complicated this loop is. 2 is almost certainly going to pay off for you. 8 might pay off for you. 1,000 is not going to pay off for you. So there is a point at which it runs out of gas. So, is there a question? Yeah.
So about retiming, does the CAD tool normally do a better job than the human designer at retiming, or like?
Yeah.
It's still better like that?
It's a good question. The best approaches I've seen to retiming are the human gets them in the right rough spot, and the CAD tool fine-tunes it. So in theory, you go, well, couldn't a CAD tool do better than a human? And in some ways it can. It knows the delays a lot better than you do. So if you look at Cordis, if you actually watch the output of its compiler, you'll see that it actually does it'll actually do retiming in multiple spots. Okay, so it does some retiming in synthesis. So synthesis is just taking your HDL, turning it into basic gates, then optimizing the gates, then it tries moving around the registers. The advantage of doing it in synthesis is that not much has happened yet, so it can move around registers basically the way I am. Like it can say, I take this register and I move it there, okay? And I just change it in the net list, and I do some checks to make sure it was legal, and I'm done. So it's relatively fast, it's not very disruptive. The problem it has is it also doesn't know the delays very well, okay? So it also is guessing, is this a good idea or a bad idea? It'll do retiming again towards the end of placement, okay? So as it's decided where everything goes, it actually has a much better idea of where what the interconnect delays are. So now it fine-tunes where your registers go because it knows the delays on each side much better, but it's more disruptive. As it does that, here I've shown you that this register there's only one copy. But if I actually had like an F3 here, so I did something like this, and there's another block here, retiming this register to this point actually duplicates it. Okay, I have to, because it's basically what retiming is doing is like taking a cut and changing it to a different cut. Okay, so I basically move this register across this logic. I have to take all the places that it crossed, and I have to put registers there. So you've duplicated the register, you have a placement, you have to reinsert those registers into the placement. That's disruptive, okay? So you now might not get them where you want, which means the retiming might just be unsuccessful, or it might make things worse, or your CAD tool might take forever. And Quartus will actually do a little more of this actually after routing. Okay, so placement has like in the latest devices anyway. We'll talk about this later in the course. But FPGAs are getting more and more register rich. So, and most of the delay in an FPGA is in the interconnect once you've pipelined a lot. So after it's actually selected the wires, it'll actually try retiming again. But now clearly it's highly disruptive, right? As it moves registers around, it's actually the routing doesn't make sense anymore. It has to fix it up. So anyway, so it's a long way of saying the CAD tool actually tries it at different levels of abstraction. And the most coarse one, if you kind of got the big picture of your pipeline and you try to put things in roughly the right spot, it still doesn't have as much insight as a human does, right? It applies sort of local heuristics, which hopefully will get it to a good spot in those early synthesis optimizations. But like not always, right? Because it doesn't necessarily see, I just got all these registers, they're not balanced, I should move them all at once. It tends to try to move them one at a time, and hence it may not see the gain. It can get stuck in local minima. CAD engineers try not to do that, right? So it may not get stuck, but it might. Does that make sense? So I tried both. Any other questions on this? Yeah?
For step 3, is retiming just to get better, I guess, like performance, like it doesn't affect your functionality?
Yeah, retiming never affects your functionality, and it never affects your latency, okay? So it's like completely invisible from the outside. It just tries to balance the registers to get you a clock period reduction. Right. And because you did this mechanically, where you just doubled up every register, you know, you did sort of a logically correct, but sort of very foolish distribution of registers, and you relied on retiming to move them around. So does that make sense? Yeah. In lab 1, you don't have to do this, but you'll see there are different compute styles. One of those compute styles, we've already talked about the streaming ones, okay? And another compute style is one where you try to share operators. It's a little bit more like a CPU, but not quite. You can time domain multiplex that. That naturally winds up with loops. You don't have to do this, but some students will wind up time domain multiplexing that because they'll actually apply this optimization to get more throughput. But the assignment doesn't actually ask you to do that, so you only do that if you're kind of just like, this is fun, I want to try it. So, yeah.
The way you're describing C-slow retiming, it sounds like it's almost like an algorithm that the CAD tools would do, but I'm assuming they don't do this because it's kind of disruptive to the...
I've seen academic tools do it, right? So there are academic tools that will do this, where they're basically trying to research this kind of optimization. I don't know of a CAD tool that will automatically do it because they worry about breaking your functionality. Quartus in its timing optimization guide will actually tell you you might want to do this, but it doesn't do it for you. The reason it doesn't do it for you is it is actually interleaving data streams and stuff, so it does require like some higher level knowledge of is that okay and how do I do that? CAD tools don't like to do anything where they're like, I just changed your design to something else that sort of might match what you want. Like they want to do like this exactly matches the input HDL because anything else is kind of chaos, right? Like I made you a design, it's not the one you asked for, but it's faster. So in like large designs that are going into big boxes, that tends to not be a happy thing for the end designer. So, okay. So let me erase this and we'll go on to something else. Okay, so that's it for streaming hardware. We talked about streaming hardware a lot. And I guess I said this C-slow retiming is not just for streaming hardware, it's really for loops. Well, it can be applied to anything, but it's particularly nice for things that have loops in them. So when I was coming here with this bucket of water, the cleaning staff, a person from the cleaning staff was out front of the room, and she asked me, "So where'd you get that water from? What are you doing with that?" I said, "I'm just going to clean the chalkboards, right?" So just I'm not violating any union rules, okay? I think the chalkboards are okay. Okay, so if you've been keeping track, we're up to compute model E. The other ones were all variations on streaming. This one's different. FSMD. Okay, so finite state machine with data path. Okay, so what is this? It's basically like, it's a lot like a microprocessor, but it's like a customized hardwired control microprocessor. Okay, so it looks like this. Okay, so you build a finite state machine. It'll go through some sequence of states, and that state machine is controlling a data path. So you choose what data path you want. So maybe I need a multiplier and an adder, because I'm doing that quadratic equation again, say. And I'm going to need usually some muxing. The whole point of this style is that I want to reuse a data path, just like a processor does. But maybe my sequence of what I'm going to do with it is pretty repetitive. So I don't really need to define instructions and a decoder and so on. I'm just going to directly control it with a finite state machine. So maybe I have the ability to put in an input into this multiplier. Got a multiplexer in front of this one too. I've got maybe some other input. And I build my data path so I can choose either the multiply or the add. I need to store some state in this, right? So for this to do something useful, I'm going to have to loop back and gradually build up results, because it again is intended for kind of temporal computation. So I'll probably put a bank of registers down here that I can write into. Okay, and then I can take data out of this register file as well, and I can send it back up here for more processing so I can get bigger computations done. And maybe I can send it up here too. Okay, and all the control signals. So what is this mux selecting? What is this mux selecting? What register am I writing to? What register am I reading from? All of that is coming out of control signals that were generated by this finite state machine. Okay, so what is this useful for? It's generally not as high performance as the streaming hardware that we've been building so far. But what it's suitable for, basically the same kinds of things that a processor is suitable for. So it's suitable for rare things where maybe you don't use it that often or you don't need that much throughput. So it can be very space efficient because you just build kind of one copy of each basic operator, and then by passing through the data path multiple times, you can gradually compute more complicated things. So that can be quite space efficient. So if you don't need a lot of throughput, that can be good. It also is useful if, again, you don't have a lot of parallelism. Maybe your computation fundamentally has loops in it. There's not that much parallelism. So this matches it well. And if you put it in streaming hardware, it would just be bigger, but it wouldn't be that much faster. Okay, and if it looks like it shares a lot with a processor, it's because it does, right? This is basically the same kind of data path that I would have in a processor. It's just I've changed the control logic to be hardwired control logic, which can be beneficial if my control is pretty simple, right? It's doing repetitive things. And in assignment 1, you're going to build a shared operator version of the computation, the Taylor series computation you have to do, which is basically a shared operator version is another way of saying finite state machine with a data path, right? So you're going to build the minimum number of operators you can, and you're going to gradually build up the computation by having a state machine control it and add everything together. And then you're going to check how efficient is this versus the more streaming style calculations that you did in the earlier part of the assignment. So you'll get experience in writing this. Is that clear to everybody? Okay, so then there's a bunch of variations that you can do on these data paths, these processor style data paths. Okay, so we could do VLIW. Okay, so VLIW is another kind of control. Now we have instructions. We're not going to use a finite state machine. We're going to actually have instruction memory that we cycle through. And, okay, so we're going to control a data path with instructions. Okay, what does the VLIW mean? Okay, so the I means instruction word, so just instructions. Yeah, so what is it? You probably have seen this in computer architecture courses. Like, why do we call it very long? Yeah.
Because I guess the different part of the instructions encode different controls for different parts of the data path.
Yeah, so exactly. So it allows us to have more parallelism in our data path because our instruction word basically encodes a lot of different control signals. So we can have a bunch of different operators. We can have more control over what things are happening. So it takes more instruction memory than a more tightly compressed instruction word, but it can express more control over more hardware units. So it can be a good option when we're building this more customized hardware. Okay, and there's a certain point, if you're doing pretty simple control, this finite state machine is normally smaller than if you built like an instruction memory and you built the decoding logic to decode what does it mean and so on, and some branching logic to decide what the next instruction should be. But as this finite state machine starts getting more and more complicated, there's a certain point at which first it's hard to write, right? It becomes a difficult design problem. And secondly, it actually eventually gets less efficient. The finite state machines, as they start getting big enough, they start getting slow and they take lots of logic. So there is a break-even point where if your control is complicated, it's actually not just easier, but also more efficient to switch to a VLIW style of control. Okay, so maybe easier, and it can be smaller than an FSM. Basically for a sufficiently wide and complex data path and operation sequence. Okay, next one. How about, so SIMD. So you guys probably heard of this too. So what does SIMD stand for? So single instruction, multiple data. So what does that mean? So yeah, so it's another instruction one. I'll give you that.
I guess an instruction that controls a single instruction that maps to all elements of the data path with performance and accomplish the data.
Yeah, so I'll just repeat that so people hear it. So a single instruction, and it controls, whereas VLIW basically is a long instruction, every piece of it could be controlling a different functional unit, so something totally different. So one piece of my instruction word for VLIW might control which register I'm reading from, which register I'm writing from, what the multiplier is doing, what the adder is doing, what this mux is doing, and maybe some more stuff, right? Because usually for VLIW, I'd have some more operators up here. With SIMD, my instruction is actually pretty compact again, because I just have one instruction saying what to do, but I'm going to do that not on one piece of data, but on a whole bunch of pieces of data. So sometimes these are called, SIMD processors are called vector processors, because instead of working on, like, add 2 numbers, you'll say add, these 8 numbers with these 8 numbers. And you can think of that as 2 8-element vectors, right? So those terms are used somewhat interchangeably. Okay, so it's many parallel execution units. And they're all the same. Okay, because they're all the same, we can use the same instruction, the same opcode to control them all, instead of having a whole bunch of different sub-pieces in VLIW. So what's the advantage of doing this versus VLIW? Right? So I could always in my instruction, if I had like 50 multipliers, just make a very long instruction word where I basically just encode, I have 50 pieces of the instruction, each of which is controlling what every multiplier does. So I could do that. I could just always use VLIW. Why would I ever use SIMD? Yeah?
Because for highly parallel like flows, it reduces the amount of memory you need because you need to store small instructions.
Yeah, so if my VLIW was just 50 multipliers and they tend to operate kind of in lockstep, like you multiply this number, I'll multiply the one right next to it, I'll multiply the one right next to it. It's kind of wasteful to encode that all individually. Okay, so you could do that, but it's wasteful. So it's basically, it basically shares control and it shares instruction bits. Which means it's smaller. Okay, smaller than VLIW. You could also hardwire the control for a SIMD, but in that case it's still smaller. Instead of having a finite state machine that produces 500 control signals, maybe a finite state machine that produces a smaller number of control signals, they get kind of broadcast to a bunch of function units. So it basically, by saying my control will do the same thing to a whole bunch of data elements every time, it factors out your control, right? I need like one copy of my control logic instead of having effectively 50 pieces of control logic to control 50 functional units. Yeah?
I guess so. Vector units, I guess, are sort of a very obvious example of SIMD processors. But would GPUs be considered sort of SIMD in this instance?
Sorry, what was the question?
I guess so. Vector units are clearly SIMD processors, but would GPUs also be considered as?
Yeah, GPUs are basically SIMD as well. They call themselves single instruction multiple thread. And I'm going to talk about GPUs in another lecture. Before I do that, I'm going to look up SIMD, single instruction multiple thread again, because it's very close to SIMD. Okay? So you can think of a GPU as using a SIMD model as well. They have a little bit of extra flexibility versus many SIMDs, but not much. Does that make sense? And I swear I've looked up the difference between SIMD and single instruction multiple thread 30 times, and it's so subtle that I have to look it up every time, and then I have to think, is this really a distinction, or is this just NVIDIA marketing? So, I think there is a bit of a distinction there. I don't think it's purely marketing, but I think I have to go look it up again in order to give a coherent answer. To first order, you could just say they're pretty darn close to each other. Yeah?
For SIMD, say like vector instruction sets, there are some certain standards that the programmer would have to like abide by. How does it work for VLIW? Because that sounds like you have to understand all the details of the entire architecture for it to work.
Yeah, then you get into how do you program it. Okay, so if you made your own VLIW, there are no rules, right? You just find the instruction word, you can do anything you want, right? So it could control 3 functional units and have 20 control signals, or it could control 300 functional units and have 1,000 control signals. You could say you got to just program it in machine code. Okay, so you got to write instructions, and you write out all the ones and zeros, and every instruction is like 2,000 bits long. People are probably not like programming your processor. If you only do a few things with it, it's okay. So normally now you'll start trying to build an assembler and maybe a compiler above that. Does that make sense? Those are like the compiler is a non-trivial task. So trying to take, for example, if you took arbitrary C or C++ code and try to map it efficiently to a VLIW, it's like an open research question, right? People, especially if the VLIW has a lot of functional units, people can't do it all that well. So they usually have to write it. They usually have to write at a lower level in order to get good performance. Does that answer your question? So yeah, you can make all sorts of hardware. Some of it, aside from efficiency implications, you also do get these implications of like, okay, now how hard is this thing to program? And that is an important thing too. So let me draw out what this looks like for a SIMD architecture. Okay, so with SIMD, it doesn't actually have to be an instruction memory. You can actually use SIMD with a finite state machine as well. Those are sort of orthogonal choices. You'll often use an instructions memory, but it could be a finite state machine where you just broadcast the control signals. But the idea is you have one control, and that control goes to a whole bunch of identical functional units. So maybe a memory block here, and the same control goes to this memory block, and the same control goes to this memory block. And each of them maybe is feeding into a functional unit. Okay, so each of those functional units is doing the same thing too. So I just broadcast this control. So it's easier to, you can see it's more efficient. I basically made the control once. It's more efficient as long as I can keep these busy, right? If I can't keep these busy, let's say I make like 16 of these, and then it turns out when I actually try to use it, I usually can use 2 on average. Okay, that was kind of a waste. So the downside of SIMD is sometimes you can't keep these things busy, but if you can keep them busy, then your control is more efficient. Okay, so it's easier to organize your control, and it's also easier to think about. Which is important when you're trying to build some new hardware. Sometimes you can just make, people are asking about VLIW, and does that get, it's a kind of a bigger canvas in a way, and can you overwhelm yourself? And sometimes you can. So this kind of constrains your design choices more, but sometimes it actually helps you converge. One of my grad students used this when he was making a matrix decomposition engine. Okay? So there's an optimization or an operation in matrix math called LU decomposition. You do basically a whole bunch of Gaussian elimination style operations, and you turn a matrix into an upper triangular and a lower triangular submatrix. And those two submatrices multiplied together give you the original matrix. So it's like an order n cubed algorithm. So lots of computation. But once you've done this, once you've decomposed a matrix into a lower triangular and upper triangular part, you can very quickly essentially solve matrix equations with it. But it takes a lot of compute. So we accelerated it with an FPGA. Okay, so we made an LU decomposition engine. It's basically doing something like Gaussian elimination, right? Take all the data in this row, scale it, subtract it from the data below, and repeat this many, many times. So because of the fact that it's taking all the data in this row, for example, of a matrix or a piece of this row, scaling it by some number means multiplying it by something, and then subtracting it from other rows is basically a whole bunch of parallel subtractions. So that maps pretty well to SIMD. You're like, I want to scale every element in here with a multiply by some number. Now I want to do a whole bunch of vector subtractions. So the way he organized this is he made as many PEs as he could fit in an FPGA, and at that time it was 144 processing elements, and they all operated in lockstep. Okay, so his control logic had to walk through this matrix, and it's a little more complicated than I've shown you here. It needs to walk through kind of in blocks and eliminate things from the right rows. But the fact that there's all this parallelism, in the end, once he figures out what to do for a certain row, it's a lot of vector subtractions from the rows below it. It maps very well to SIMD. So it makes it more efficient, also made it easier for him to think about, because he could see now the control was kind of simpler. So that was a good example of building a SIMD architecture. And yeah, there's a good question on GPUs. So this is basically it's not only used by like people making custom hardware. SIMD is basically used in GPUs. And it's also used in modern microprocessors. So you'll see that in one of the readings this week. So modern processors can also use a limited amount of SIMD if you program it appropriately, because it is a pretty productive, efficient programming model. Okay, so another thing you can build is a soft processor. Okay, so most FPGA designs Actually have processors in them as well. They don't do everything in like custom logic. So you can build anything out of an FPGA. So you can build a processor. So if you build an FPGA out of the LUTs and DSPs and wiring, etc., that's called a soft processor. And everybody's got one, right? So Altera has one called Neos. Xilinx has one called Microblaze. Microchip uses RISC-V, and increasingly, because RISC-V is open source, kind of everybody has a version of RISC-V for soft processors. So what are these useful for? Well, what would you use a soft processor for in an FPGA? Yeah, what did you? Yeah, so you'd use it for like lightweight stuff, and I think that's a good idea. So lightweight tasks. So some things that are lightweight tasks are like housekeeping and setup. Okay, so what do I mean by that? Like somebody's got to get the system ready. Somebody has to clean up the memory at the end or handle unusual exceptional conditions. Those usually don't have to be all that fast. Their logic is often a bit complicated, so they're a good match to a processor. You can use this. Well, anything else you could use this for? What do you think?
Some security stuff.
You can use it for security. It depends how high performance it is. So you could use it for kind of, again, the setup or the housekeeping. Like a lot of it is security. Maybe there's some key exchange that happens and some protocol. If it was an encryption of network traffic, then that's actually really high data rate. Okay, so if you were encrypting all the data going over a network, which FPGAs are used to do, that's really high data rate, and that you'd want to put in streaming hardware. Okay, but the exchange a key at the start of some transaction before you do your Bitcoin mining, that would be fine, right? So maybe security sort of setup, right, but not like hardcore line rate encryption. Yeah, any other ideas? So one of the other things you can use is you can use it for hardware control. Okay, so if we build a big data path using SIMD, or we built a data path and we were thinking of controlling it with a finite state machine, but the finite state machine is getting really complicated, we could control it instead with a soft processor. And the nice thing about a soft processor is we can kind of build as many of them as we want. We can build them wherever we want. They're not all that big, so they don't take very much of the chip, and you could build a whole bunch of them, and you can kind of hook into them in different ways. So so if your control's not that fast, and that means probably it's controlling like a bunch of hardware units with SIMD or something, then you could use them to actually be the control logic. Okay, they're probably not for heavy lifting. Or like for the heavy computations. Okay, so what I mean by that is like the high speed computations you're doing, it's probably not a great idea to be trying to use in a soft processor. Doesn't mean nobody tries. There are academic works where they take an FPGA and they put 1,000 or 2,000 or 3,000 soft processors in it that are highly optimized, so they don't take much of the chip, and then they have them all collaborate. So they're all connected with some custom soft interconnect. It's basically a network on chip that they build out of the FPGA logic resources. So they've got a very highly many-core processor in an FPGA, and they try to get performance out of that. I've always been skeptical of that, although there are people who've done it and gotten reasonable performance. But it seems like a pretty difficult path to me. Versus, why do you think that is? Or maybe you have a different point. I'm not sure. But,
sorry, no, I had a question.
Okay, so maybe before that, so I'm a bit skeptical about this technique that some people use of I'll use soft processors, I'll just put a huge number of them in. I'll put 1,000, 2,000 of them in, I'll really optimize the heck out of them so I can fit a lot in. What do you think?
Coherency and is a big problem, and sharing of resources.
Yeah, programming them gets hard, right? Because usually they don't have coherency. They're usually programmed pretty close to the metal, right? Because if you start having a lot of coherency protocol about who's got the memory, and I'll just have a global address space, it's so inefficient that it's like, why am I doing this? I made 2,000 processors and then spent tons of logic where I basically just could ask for things by memory address, and then all the logic figures out where is it really. That's kind of like, again, moving back towards centralized storage. It's very inefficient. It's probably not a smart idea. So you're right. So usually they don't build coherency. They instead say the programmer has to manage where is the data, which is probably more logical, right? They say the data is distributed and the programmer needs to know where it is and has to explicitly ask for it by location. But it does make it hard to program.
And it's kind of an oxymoron. You're taking a very scheduled processor and you're forcibly parallelizing it. So it's always going to be difficult to make it.
Yeah, so I think they wind up with like kind of an amphibious car, something that's a bit hard to program, but also not that high performance, okay? The reason I say amphibious car, I was visiting a customer years ago when I was at Altera, and I was visiting with a member of our sales force. And at the time, Altera had this product called hard copy, which meant you could take your FPGA design and Altera would help convert it, well, Altera would convert it to an ASIC, okay, that used some of the FPGA blocks, so it was a bit easier than if you moved it to an ASIC yourself. And this person asked, what if you gave me a chip that was half each, half FPGA and half hard copy? And the salesperson said, that's an amphibious car. And I thought it was a great answer, because without me telling you anything more, you know it's a bad car, that's a bad boat. Which is exactly the right answer for that question. Because if you make something that's half ASIC and half FPGA, it basically has half the inefficiency of an FPGA, and it has all the design complexity of an ASIC. So it is like an amphibious car. It's like you've got not the best of both worlds, you've got the worst of both worlds. So I'd say this, I mean, it's a little probably too harsh. People have done some interesting things with this, but you get the difficulty of programming a massively parallel array of processors, and you've given up a ton of performance because you have 2 levels of programmability. Okay, so what do I mean by that? So an FPGA gives up a lot versus an ASIC in terms of efficiency because of the fact that it has, you know, programmable muxes, programmable logic blocks, etc., instead of just wiring things together, right? Like taking the exact gates you want, wiring them together with metal. We're going to study that you're going to start getting into it in some of the papers next week, and then the week after we'll talk about it more. But that's not a small cost. It's on the order of magnitude, right? It's like around 10x bigger. And now a processor also loses a huge amount of performance because instead of just doing something, it basically has an instruction word that says, configure all these muxes in the following way, and do this one or maybe a few things, maybe even more than a few things with SIMD. But I basically have a data path that has more muxing than I normally need, and I have to decode this instruction to say how to configure the data path for every operation. That's what one of the papers that you're reading this week talks about, and that's also a very large cost, like an order of magnitude or more in efficiency. Now what you get for programmability is like you get to market much faster, and you avoid very large NREs, right? Like, so the cost of a completely custom chip, depending on the process technology, is maybe $30 to $100 to $200 million. So if you have programmability, you avoid that. But there's 2 levels of programmability. The second level of programmability doesn't buy you that much. One level of programmability means you don't have to make your own custom chip. The second one just kind of changes your programming model some. But each of them costs you around 10x efficiency. So this is kind of like, you know, on first order, like you've given up maybe 100x efficiency. Now, when people do this, they make really big arrays of soft processors. They then try to micro-optimize them and get back some of that cost. But it does seem like kind of a strange thing to do. So I think the best use of soft processors is for these lightweight tasks, for controlling hardware units, where you kind of use them for what they're good at. They're easy to program, and as long as they're not the bulk of your design, the inefficiency they bring doesn't matter as much. Yeah?
For like interfacing like complex IOs, like those could be also you could also use. Like,
Yeah, I'm actually going to give you an example of that.
you don't really need, like if you need more performance, well then you would have to drop it, but at least you don't have to like pin yourself with like, I don't know, making a DDR6 or
I'm actually going to use that as an example. Okay, so I'm just going to write that down though. So for order of magnitude, if you want to think of what is the cost of making something programmable versus hardwiring it, it's around 10x. Okay, so this is around 100x. There's one academic paper that I once saw, which amused me because what they did is they took an FPGA Okay, so I took an FPGA. It's like a real FPGA. It's like a Xilinx or Altera FPGA. So it's programmable. It's lost maybe 10x efficiency versus you make all the gates. On that FPGA, they built a virtual FPGA. Okay, so they don't actually want to use the LUTs and wires in the FPGA. They use the LUTs and wires to make virtual LUTs and wires, which is now another factor of approximately 10x. And then on that, they ran the soft processor. So I was a reviewer of this paper, and I was very tempted to just basically call this Inception. So if you've ever seen the movie Inception, with every layer they go down, they things get 10 times slower, right? And that was effectively what their paper was. It was completely unclear to me, like, why would you do this, right? Like, your goal seems to be like to just keep going slower and slower and slower with more and more layers of programmability. So, I'm sorry?
Are they trying to simulate CGRA? Like,
What were they trying to do?
simulate CGRA, force field, manipulate?
No, they were trying to simulate an FPGA on an FPGA so that they could have control over the FPGA architecture without making a custom one. So they'd done that in one set of papers. And then they said, well, it still can be hard to design FPGA logic, so let's make a soft processor on that. But I mean, it was quite baffling, right? The motivation for doing this seemed quite strange. So, yeah.
If you have an FPGA with a hard processor and you're just using it, or you just want to use it for control, what would kind of be the benefit of having a soft processor?
Yeah, so it's a good question. So I can't remember. I think I've got this in my notes later on. So FPGAs also now have hard processors because they basically remove a level of programmability, right? So they are more efficient. They'll clock faster. They take less area for an equivalent soft processor. So they have hard processors, and people use them, right? So if you have a hard processor available, you'll probably use it first for housekeeping. You can also use it to do some of your hardware control. People still use soft processors because they often need more processors than an FPGA architect has to decide how many hard processors and where do I put them. So for lots of people, that's going to be fine, right? They've got enough hard processors. They don't need to make any soft ones. But there are other people who run out. Okay, so they're in the wrong spot. They're off in the top corner. I want it over here. I need 5 of them. You built me 1 of them, right? Or 2 of them. I need more. Does that make sense? But that also pushes you towards the soft processors now that you should make are probably smaller and lower performance because the first few tasks that might need, whatever needs the most performance from a processor, you're going to put in the hard processor first. And only once you run out of those are you going to start putting things in soft processors. Yeah?
Like using a soft processor would be equivalent to doing like multiple instruction and multiple data, right?
You can do anything you want. Okay, so you could make, and usually the soft processor, there are a lot of different soft processors. One of the nice things is you can just program in any processor you want. So let's take Altera. Altera has Neos. Neos has like a small version and a sort of a bit bigger version that's a bit faster, it's more pipelined, and an even faster version that's more pipelined still. They are still relatively simple processors. They don't do multiple issue, for example, like they issue 1 instruction a cycle and so on. You can build even faster soft processors, but they start getting big. So usually, if you're going to start getting into higher end, superscalar, out of order, like go for a hard processor. Those are starting to become large enough that they're no longer lightweight and they probably don't make that much of sense. You can also add SIMD units to them. But again, you probably, if you're going to do a lot of that, well, you can use it to control a bunch of custom SIMD units like this. So that's fine, because your processor is a relatively small part of your data path. Does that make sense? So that is one of the advantages of a soft processor. You choose whatever instruction set, choose like how fast you need it to be, hook it in to control some custom hardware, et cetera. So its flexibility is its strength. And they do get used extensively because of that. The kind of, an expensive soft processor might be a couple thousand LUTs, like a relatively fast soft processor, and a cheap one might be like a few hundred LUTs. So in a device that has like 1 million lookup tables, a few hundred LUTs is not a lot, right? And if it makes you more productive to do, some setup in that, and you need 6 of them, 1 for this IP block, 1 for that IP block, you're not going to worry about it too much. But if you try to do most of your processing in it, it's going to add up pretty fast. Does that make sense? Okay, so let's talk a little more about processors now. So you can just, take a standard RISC-V processor or Neos or Microblaze, which are ones from the vendors, and just use it. But you can also make your your own custom augmentations to them. Okay, let's see. Okay, so let's talk about augmented processors. Okay, so there's two basic ways that you could take a soft processor and augment it in kind of a unique way, like where you could add SIMD units and so on, but we already talked about that. So I'm talking about something more different than that. So the first way is called custom instructions. Okay, so what does this look like? So let's take most of the soft processors you'll get from the vendors. Let's take Neos or Microblades, which is Altera and Xilinx. If you take the kind of middle soft processor, the one that they say is sort of the standard version, it's a classic 5-stage RISC pipeline. Okay, so it's got fetch, it's got decode, it's got ALU, it's got memory, and it's got write back. How many people built a processor like this in a computer architecture course? Okay, or saw one like this in a computer architecture course? Okay, so quite a few. So the reason that they use this is it's a kind of the sweet spot. Like this is quite efficient in terms of area, of throughput per area. This is probably like the minimum of the throughput per area curve. So that's why it's their default. Okay, so what these custom instructions do is they basically, you define, okay, they reserve some opcodes. Some opcodes they just don't use, okay, for normal operations. And you can, it's different in the different vendor tool flows, but you can basically go in and say, okay, this opcode maps to a new functional unit that I basically built. So when you see this, I want you to, the decoder to send it to my custom hardware that I built and put in the FPGA. And it'll do that instead of the regular ALU step. And then it'll normally go into the memory step again. Okay, so it basically is like you extended the ALU step of the pipeline. And it's not that hard to do, right? You say, what's the opcode? You give it the hardware, and it gets stitched right into the pipeline. Okay, what do you think this is good for? What do you think?
Well, one example is like, let's say you want to, oh, I don't know, like, there's a like certain instruction that's taking like a lot of time, like I don't know, floating point operation.
Okay, so you find some operation that's slow.
And then you can put it in custom.
Okay, so you basically, and you said floating point. Okay, so floating point would be a good example. Back in the days when we didn't have hardware floating point. So now processors usually have hardware floating point in there, so it's no longer a good example, but it would have been before. But you try and look for something kind of like that, okay? And what I'd say is floating point, how many inputs do you need to floating point operation usually? So usually you need like 2, right? Like add 2 floating point numbers, multiply 2 floating point numbers, and you produce 1 output, okay? Which kind of fits nicely in the processor pipeline. That's kind of generally how most processor instruction sets work. Take 2 things, produce 1 thing, right? So it's useful for what I call fine-grained ops. Okay, so what I mean by that is like, yeah, this pipeline wants to send you 2 pieces of data, for example, from the register file, and you produce 1 output that can go back to memory or the register file. So if you can do that, and you're a lot faster than the regular instructions, you become a useful custom instruction. I can give you an example where this has been used pretty successfully. It was used, floating point is one example, right? So back before soft processors had floating point, but now often you can just ask for it, so we don't really think of it as a custom instruction in much. But in that same vein, there's another set of instructions this actually has been pretty useful for. Yeah, what do you think? So multiply, accumulate. Yeah, so multiply, accumulate it could do. The thing is that that's kind of gotten folded also into the baseline ALU, right? Where you like your multiplies, or now you have multiply, accumulate operations. If you only had a multiply and an accumulate, then you could put a MAC in. Yeah, so if you had a complex active, that would be a good one. So maybe you have some complex Gaussian ReLU or GelU that's a bunch of math. That's actually a good one. I didn't think of that. Okay, so complex activation. The reason that one's a good one is you think of the activation functions in machine learning, they usually only take in one input and they produce an output. But the function can actually be kind of complicated for some of them. So that's actually a good example. I don't need very much data, but I need to do a bunch of compute. Thank you, right? So the Gaussian, there's a function that's used a lot in transformers called GelU. It's like a Gaussian version of ReLU that's actually a lot more compute. And that would actually probably be a pretty good example for this. Another one that has been used a lot is CRC. So FPGAs get used a bunch for security and encryption. So the security and error correction both tend to use a lot of cyclic redundancy checks, right? They do a lot of XORs, a lot of parities. They shift everything over to, they XOR them again, then they add in some random bits and they XOR the whole thing again. What that is actually there's not a whole lot of data going in, but there's a lot of operations. Those operations can be done by a conventional CPU, right? You can basically do a whole bunch of shifts, a whole bunch of lookups, a whole bunch of XORs, but you might need a long sequence of instructions. And if you had a CRC operation for the exact encryption standard that you're using or the exact error correction standard you're using, you could collapse a long chain of instructions into one. So they have been used pretty successfully for that. Okay, so, but notice I said fine-grained operations. What they're not great at is kind of, you might think, well, maybe I'll use this. We're talking about transformers. So transformers have these activation functions like GelU. They also have a ton of matrix multiplies. Okay, that's actually the heart of the compute inside the transformer, is a whole pile of matrix multiplies. Also a whole pile of softmaxes. So maybe I can map those to this custom instruction, right? Maybe my custom instruction can be like matrix multiply. Any challenges with that? Yeah, what do you think?
I guess you're extending, if you just want to maintain a 5-stage pipeline, you're prolonging the cycle because you're assuming you want to do it in the cycle.
Yeah. Okay, so let's talk about some of the challenges with coarse grain. Okay, and maybe we'll use multiply as an example. Okay, it's nothing special about matrix multiply, just maybe gives you an idea of what we're talking about. So one problem is, which is it's not catastrophic, but it's annoying, is we're going to stall the processor. Okay, so especially if this is a big matrix multiply, it's not going to execute in one cycle, right? Matrix multiply is an order n cubed operation for matrices that are n by n. So this is, unless we do a really small matrix, this is going to run for quite a few cycles. While it's running, these are relatively simple processors. So we're going to stall, right? We're going to say, this thing's not done yet, still working, the processor will stall. It's not the end of the world, but it does mean that our processor is basically feeding data to this custom unit, and then as soon as while the custom unit is chewing away for maybe 500 cycles, the processor has to stall. So we do lose the possibility of parallelism. Might still be a win, but it's kind of annoying. Yeah?
I used like Neos too, like a year or two back. There was like multi-cycle instructions, so like you could just like send it stuff, and then the CPU would like keep going.
Which processor was this in?
It was in a cycle.
Is it a cycle in 5? So I think Neos actually stalls. right? So in other words, you can say, like you can send it an instruction and it will basically stall the pipeline. Now you could also say, I'm not going to stall, right? And you'll just negotiate to get the memory when it comes back and tell the programmer, make sure that you're not depending on this result. So I guess you're right. It's not, okay, or make processor a bit more complicated. And maybe Altera's done that with Neos now. Which processor were you using, actually? Okay, interesting. Okay, so maybe they're not stalling. Although if you're depending on this, you may still run out of things to do, right? These processors don't have fancy out-of-order mechanisms because they're too hardware expensive. So if it's not going to stall, you're going to have to keep track of that that's okay. Do you know what I mean? Because the processor is not going to keep track of when is it okay to get instructions again. So the programmer is going to have to figure that out. Yeah?
At this point, would it be better to just make this custom logic like a memory map peripheral that we can code from time to time?
Yes. So that's where I'm going next, right? So that's actually a very good insight. So the stall is one downside of the way we've integrated as a custom instruction. The other downside is basically ports. Okay, so by hooking into the pipeline like this, we kind of inherit the ease of use of the pipeline, but we also inherit its limitations. That our pipeline was built to send, for example, 2 inputs and take 1 output. It doesn't actually match a matrix multiply very well at all. Like, I need to send it a whole pile of inputs, so I want it to do a matrix multiply. I need to send it 2 matrices, and I need to get back a 3rd matrix. In order to get much efficiency, I want those matrices to not be super small. Like if you say the matrices are like 2 by 2, that's so small that you're not getting much compute done. You really want them to be, 8 by 8, maybe 16 by 16, something bigger where now there's actually quite a bit of data getting transferred to this, into it and out of it. It doesn't match your ports very well. You could make more ports to the register file, right? So this is where we're fetching, this is where we're actually reading the register file somewhere in between these 2 phases. I didn't actually put an RF in this, but somewhere in there we're reading the register file. If I want to get a lot more data from the register file, I have to make my register file a lot more complicated. And that basically is not going to fit the rest of the processor very well. So they just don't allow it. They're like, no, you're hooking into the processor, you're a custom instruction, you get your 2 pieces of data. And it basically just doesn't really work for something coarse-grained like matrix multiply very well at all. Okay, so our ports are limited by the register file. Okay, so we have this central storage bottleneck. Okay, so the other way that we could do this isn't the only way we can augment a processor. We can augment a processor with a coprocessor. Okay, so this is an alternative. Okay, what does this look like? So we have our processor. It could be a soft processor. This could now be a hard processor. If this is a hard processor on an FPGA, we normally can't hook right into its pipeline, right? Like it's not accessible. But for either a soft or hard processor on an FPGA, we can hook into it using a standard bus. Okay, so it could be AXI. That's the most common one now. Altera also has an alternative called Avalon. And we can basically send commands over this bus, right? For example, this could be a memory mapped bus where we read and write from certain addresses to send commands to a peripheral. So we can make a coprocessor, so a block of logic that also has an AXI interface. We map certain addresses on this bus to registers in this coprocessor, and now we can basically control it. We can send it commands, we can read back status. And this coprocessor can talk, we could choose to have it talk directly to memory. We can do anything here, right? So this isn't just logic. It could also talk to on-chip memory as much as we can fit or want. It could talk to off-chip memory. So this could be DDR, anything. So what we get here is we get more memory. Because it's basically unconstrained. It's now up to us. So we get more memory and more bandwidth. We can get more concurrency. Okay, so the way we can get more concurrency is normally the way these are hooked up is you send you write to a certain address, goes into this register here, and maybe that says go. And when it's done, it either just stores a done flag here, or maybe it writes back to some address and tells you, or interrupts you to say I'm done. But it's fundamentally, you send it commands and then you can keep going, right? There's no reason the processor has to stall. It could wait around and read some register over and over again for a done bit, but doesn't have to, right? It could just periodically check, could wait for an interrupt, could use all sorts of different techniques. Yeah?
Modern FPGAs with hard processors provide an interrupt unit that we can hook up to our own hardware. So
Yeah, and then in a hard processor, this is also a more, in a soft processor, you can do this, or you can do this. You just build whatever you need. In a hard processor, they've essentially pre-built, this piece, right? Along with interrupt units and so on. This is part of what makes hard processors more expensive. The hard processors and FPGAs tend to be a lot more full-featured than you would build with a soft processor, but they're built out of gates, so they're still not too huge. But you get a bunch of this functionality pre-built for you if you do that. Okay, so basically this means there's bigger potential for this because it doesn't, last thing is it doesn't operate in lockstep. Right, so these are basically running more asynchronously, and you can choose at what point you want to resynchronize them. Okay, so maybe I'll go through. Okay, let's take a break for 10 minutes, and I'll go through an example of using this. It's hot in this room. So we'll give a design challenge to the class. If anyone can figure out how to keep this room cooler, you get like bonus 15%. So, okay, so I'm going to give you an example of choosing a compute model. There's a real example where it's an example where we did it two different ways at Altera with two different compute models. So it's memory interface calibration. It's kind of an interesting application anyway. So let me describe what the application is. Okay, so you have a design. And so this is logic that you make. In this case, we're going to put it in an FPGA. I want to talk to off-chip memory. There's a whole bunch of different related off-chip memory standards. So there's DDR3, 4, 5. There's HBM, which is a stacked memory technology, but its interface is basically the DDR interface again. There's something called reduced latency DRAM, which is lower latency, but again uses DDR style interfacing. So there's a whole bunch of different memory technologies that are similar in how they talk to a chip. So I'm going to give you an example from DDR3, but it would be quite similar with any one of those other ones. So you have a design and you want to talk to DDR memory. Okay? So you talk to it in two pieces. You have a controller. So your design basically issues like, I want to read from a certain address, I want to write to a certain address. The memory controller knows how to translate that into commands that DDR chips understand. So DDR chips actually take lower level commands that are things like activate a row, okay? So that takes data out of the DDR, some of the DDR capacitors and puts it into latches called sensamps, okay? So that's activate. Then you might say, okay, now I want to read from some of those latches, and that's actually a read command. So the controller handles that. You just say read. The controller knows that DDR doesn't really know what to do with the read. It has to be a sequence of commands, so it makes that sequence of commands. And then the controller talks to a PHY. So PHY is physical access layer. And that actually understands the low-level electrical and timing standard of DDR, which is complicated because all these memory chips, their whole goal is to be cheap, but also provide a lot of bandwidth. And in order to do that, they have fairly complex electrical and timing standards to try to move data to another chip. Okay, so from this PHY, so the PHY basically takes these low-level commands and figures out what do I actually do in terms of signal waveforms with very precise timing and so on to make this all work at high speed. So the particular example I'm going to give you is talking to DDR3, but it wouldn't be much different for any of the other variations. and is talking to it at 1.6 gigabits per second. Okay, so the time window between data is only about 60 picoseconds. So pretty fast, pretty easy to get wrong. All of this part is on the FPGA. Okay, so there's the design you made, and the memory controller and the memory PHY are normally given to you by the vendor, right? So Microchip or Altera or Xilinx build this for their chips. They're highly configurable because they want their chips to talk to all these variations of DDR, right? So DDR3, 4, 5, high bandwidth memory, low reduced latency DRAM, etc. Okay, so how do these actually talk? Okay, so the way that all of those DDR-related standards work is they're called a source synchronous standard. Who's heard of that before? Who knows what a source synchronous standard is? Okay, so maybe 2, 3 people. Who doesn't know what a source synchronous standard is? Okay, and the other people are like, I'm slowly zooming on the people who will never answer a question. By the end of the course, I will know who you are. So you have to answer at least one question, or you're going to be like, oh my gosh, he's like figuring out the Venn diagram, right? Okay, but that's good. Okay, so what I'm going to tell you then is not known by most of you, which is good. This is like, there's only basically 2 ways to do high-speed I/O. One of them is source synchronous. That's what DDR uses. Okay, so it's actually useful to understand how this works. So what source synchronous does, I'm going to do it in the DDR standard, but it's kind of, this is the way source synchronous always works, is so DDR sends a strobe, and the strobe is called DQS. Okay, so it looks like this. Okay, so this is the strobe. And when I'm doing, let's see, so I'm going to, basically when I'm doing a write to the memory, I'm going to send it this strobe along with all the data. Okay, so the FPGA will send it the strobe, and it will also send it the data, and the data is called DQ. And it'll send one strobe for 8 bits of data. Okay, and the data changes away from the clock edges, or the strobe edges. Okay, so that's what this is drawing. Let's see if I drew this properly. Okay, so the idea is that the edges of this strobe I can use to sample the data. Okay, the difference between a strobe and a clock is that a strobe can stop. Okay, a clock doesn't stop; it normally is just free running. A strobe is like a clock, but it only goes up and down when you actually want to send data. So you can think of this as like a clock, but it gets stopped to save power when you're not sending something. And in DDR, the double data rate actually comes from the fact that we use both edges of the strobe. So on a rising edge or on a falling edge, we take whatever data is there. The reason there's one strobe for every 8 bits of data is we need to align this strobe very precisely with the data. Memory chips are built to be cheap, so what they do is they just take this strobe signal and they just use it to sample the data. They expect that this strobe is in the right spot. Okay? And it turns out that if you made the, so memory, normally if you have a DIMM, it's say 64 bits wide, you can't make one strobe for 64 bits. There's too much skew between them, so that's why you have like one strobe for every 8 bits, because it has to be lined up very precisely, and it's just too hard to line up 64 bits that precisely. So the standard basically says, no, send one of these for every 8. But I would now repeat this pattern, for example, 8 times to get to a 64-bit wide interface. And you get all of that just by asking in the Cortis or Vivado, you would say, give me a DDR controller for this interface standard at this speed, and it would build you the IP to do this. Okay, so you wouldn't worry about it. You'd talk to it with AXI, with these kind of higher level read and write commands, and all this translation is happening automatically for you. Okay, the part that's hard with this is getting this lined up. And all of the complexity of lining this up is the problem of the FPGA, or if it was a processor, the problem of the processor or the GPU. To keep memory chips cheap, they just take whatever you give them and they use it. Okay? The goal of all these memory standards is make this cheap, but make this standard fast. So all the complexity gets pushed back this way. Okay, so what is that complexity? So it turns out, when you make chips, they have process variation. So your transistors are not exactly what you thought they were. The wires are not exactly what you thought they were. the circuit board is not exactly what you thought it was. It has skew on it. Different circuits slow down or speed up differently as the chip heats up or cools down. And this memory chip has relatively poor specs. It doesn't actually, it basically doesn't guarantee that inside of it, all of these data paths for these 8 bits are the same delay. So what that means is that if you just send 8 bits of data and a strobe that you think is lined up with it, it will never work. Okay, like the memory chip will never properly register the data. So what you have to do is you have to calibrate. So you have to adjust the delay of basically every DQS. And for a 64-bit interface, we'd actually have 8 of those. And every DQ bit until it works. Okay, we can reliably send data, write it, read it back, etc. Does that make sense? Okay, hopefully I think you're with me. Okay, so what does this look like? So the data path is, I mean, it's configurable. This is an FPGA, so you can ask for all sorts of things, but commonly it would be 64 bits wide. And the speed it's running at, at the I/O pins here, basically these edges are they're running at 1.6 gigabits. Okay, so it's 1.6 gigahertz that this data is changing at. Okay, so that's our data path. Okay, what's the control logic? The control that actually figures out how should I shift all these DQSs and all these DQs and so on for reads and for writes is actually quite complicated. Okay, so the control is this complex calibration algorithm. This is complicated because, well, it's actually like some secret sauce. Like you can't actually go find somebody publishing their best calibration algorithm. You write things to this with certain timing. You read back data. You see if you get what you wrote. If you didn't, something went wrong. You don't know if it's the read or the write. You try something different. You mess around with that a lot. As the chip heats up, you have temperature sensors. You try to guess what you should do as the chip heats up, et cetera. So it actually turns out to be quite complicated. And you're trying to do this at high speed. Everybody's competing to go to the highest speeds. So if you go to DDR4 and DDR5, the speeds are higher still. And there are a lot of different variations. I talked about all the variations of DRAM and so on. So you actually have to work for all those. So there's also a lot of programmability. So it means this algorithm is pretty complicated. And you don't know exactly what it is when you start. You actually start writing an algorithm, you try it in the lab, you see if it works, you mess around with it. The new standard comes out, your algorithm's not good enough, you play around with it some more. So it's also not a defined, just do it once and forget about it. This is going to be a living algorithm. Yeah?
So talk about the strobe. Like, is that what, so we're buying RAM, they typically have a speed with megahertz, and then they have a clock, CO, for example, CO18, CO36. Is that what the strobe is?
So DDR standards are sort of, you have to read them carefully. So a lot of companies will brand their DDR by this data rate. Okay, so if you get DDR 3300, it actually means 3.3 gigahertz. The clock is actually half of that. Does that make sense? That's the rate at which the edges are occurring when you count both edges. If they give you the clock as half that, that number is smaller. Marketing likes bigger numbers, so usually they'll actually say something like DDR. So usually this would be called, for example, DDR 1600. Okay, even though the clock frequency is really 800. Because the data transfer rate is 1.6 gigabits per second, they're going to call it DDR 1600. And it's because marketing, if engineering says, well, it's really 800 megahertz, so we should call it 800. Your competitors call it 1.6. We lose a lot of business, but we seem honest. Marketing doesn't like arguments like that. They just make fun of you and they say, okay, it's at least DDR 1600. Could we call it DDR 3200? Right? So. Does that answer your question?
Because like because there's like two numbers now. Like when you're buying RAM, there's the headline numbers like the 3200 or 3600, and then there's a CL, which is they
Oh,
call
CL is column latency.
column.
You're talking about CL?
Yeah.
CL is, okay, so now you're getting into the internals of a DRAM chip. So I told you that when you actually read from a DRAM, you actually have to do it in two phases. There's what's called the activate command, which basically reads an entire row of data. Internally, the DRAM's a bit more complicated than this, but you can think of it as being a 2D array of like capacitors connected to bit lines. You send an activate command, basically a row of data is sensed. Okay, so basically sense amps are differential amplifiers that sense was that a little bit of a negative charge or a little bit of a positive charge in that capacitor, and they store it in latches. And you get a whole bunch of data in latches. Maybe you get 8 kilobits of data when you do an activate. And then you can read it out with basically read commands, which actually read from those latches. And the CL is basically what is the latency from the read command to the data coming out. Okay, so it's a measure of latency, which for PCs where they're latency sensitive, like processors usually can't find enough work to do if they're waiting a long time for memory, so it's another spec that people would like a lower CL. The most important spec is what's your bandwidth, which is tied to this rate, but another spec is what is the latency for getting data out of those latches, and that's what the CL is. Does that make sense? If you're building an accelerator and you do a good job, you shouldn't care too much about CL, because you should be basically, you should have designed it to be doing so much work that it's kind of got data coming in, going into like those FIFOs that we talked about, like that streaming hardware FIFO. It's going into those FIFOs and keeping the compute units fed, so you don't really care about that CL very much. What you care about is the bandwidth, because that's going to affect how fast you can stream the data on chip. Yeah?
So you talked about how when you design like memory, you have sensors that sense the temperature of your circuit and kind of adjust the algorithm based on that.
Yeah, you actually have those on FPGAs. So there are temperature sensing diodes on modern FPGAs to actually allow you to tell what's the temperature of the chip. So the memories may have those too, but the memories are built to be cheap. If they can move all that complexity to the other side, they do it.
Yeah, what I'm thinking about is if you're trying to line up the DQS with DQ, what if you have the trace when you send it to DDR, if you can measure a returning trace back to some control logic that kind of like measures, okay, how much latency was the round trip, and then adjust based on that. Is that something that they use for that algorithm?
Yeah, let me think about that. I mean, the algorithm's complicated, so I don't even know if I can describe all of it. But basically, all you can do is send write commands and read commands. You can only send the regular commands to the DDR, that's all it understands. So you can try all sorts of commands with all sorts of different timing, and then you can read stuff back. Until you can write reliably, you have this problem of like, if I didn't read it back properly, did the write fail or did the read fail? What you usually do is you try sending it some data very slowly. Like you just hold the same data pattern and you just strobe it over and over and over again. And you go, I don't care what's happening. I think I got this number in. And then you try to read it back.
Right.
Does that make sense?
No, I mean, but when let's say you taped out your chip and it's an ASIC, so
Yeah.
you can't adjust your algorithm on the spot.
So ASICs have to build this algorithm in too. If you had an ASIC and you did not build a calibration algorithm, your ASIC does not work, your CEO is going to fire you. Like I promise you, because first of all, it's not going to work. You're not going to be able to talk to DDR, and they're going to say there's a problem with the calibration, and you're going to say I didn't use calibration, and they're going to fire you. Okay, so and this is an example where in an ASIC, they're going to have a very similar problem to what I'm talking about here. If they take this calibration algorithm and they reduce it to like just hardwired logic with no programmability, that was a career decision for somebody, right? Like somebody was like, I am feeling so confident. Like, I don't care, it's going to work. Right? So it's like super risky. You really want to be able to change this algorithm.
So it's a mix between like hardware and maybe software as well?
Yeah, so where I'm going with this, okay, this is all kind of set up, but it's also kind of interesting because now you actually understand one of the two fundamental ways that people send data quickly, right? So at really low frequencies, you can have a system clock. A system clock is basically just a clock that goes to everybody. Everybody uses the same clock. You send data and you just get it on that clock. That doesn't work at high speeds, okay? There's too much clock skew, it doesn't work. You go to higher speeds, you go source synchronous. Source synchronous is you send clock and you send data with it, or you send a strobe with it, and you can use that to sample the data. What is nice about this is the circuitry to create this. While this calibration algorithm is complicated, the circuitry is pretty efficient. and it's low latency. Okay, so memory, we actually do want low latency to it. And this hardware will not add very much latency. So that's all good. This is why it's used for, source synchronous standards are used to talk to off-chip memory. As you're going to see, like this calibration algorithm is necessary to make them run at high speeds. And if you start moving this DRAM chip further and further away, where now the traces on the board get less and less predictable, your speeds will go down. Okay, so this is a good way to talk to memory as long as it's relatively close. And yeah, it's one of the two dominant ways we talk to things quickly. Does that make sense? Okay, so I guess all of this though is set up of, I've described a problem, right? This is a problem, like it's an IP core problem. We now need to make an IP core, like a block of hardware. We need to choose like a way to organize this computation. Like this is a computation. How do we talk to this memory? And we have to calibrate it. Okay, so we need to make a calibration algorithm. Once it's calibrated, so when you actually turn on an FPGA, if you have a DDR IP core in it, it will calibrate without you knowing. Part of the chip powering up is it will actually calibrate to the RAM, and only when it's calibrated will actually start accepting read and write commands from you. So there is some period that's relatively short where it actually won't listen to you. Okay, it's calibrating in that time. Okay, but how do you organize this? So we've talked about a bunch of compute models. What do you think we should do to make this work? Any ideas at all? So, yeah, what do you think? So you think a coprocessor is good. So I like the idea. Why do you like coprocessor?
Because we want to send not able to interrupt the data instantly.
Yeah. So it's a great example for a coprocessor because this data path is fast. Okay, so 64 bits wide, 1.6 gigahertz. Okay, that's really fast. That's like high speed even for hardware. So we have to make this with like basically streaming hardware, like the fastest way we could possibly make it. And after we calibrated, we're just going to have, this streaming hardware is what is going to be talking to the user design. But basically saying coprocessor, which allows you to move this control logic, which is complicated and we don't even quite know what it is yet. Right? When we start, we don't know what the algorithm will be, and we expect it to evolve a lot over the years. We move it to software, okay? Because that's going to be our most productive way to make a complicated algorithm. So that's actually exactly what we did, okay? So the architecture that we chose to use was a microprocessor plus a coprocessor. Okay, so what we did is we used Neos, which is Altera's soft processor. Okay, so it's a microprocessor, it's soft logic. We don't actually need it to be that fast. Okay, so this calibration algorithm can take, like even if this takes like millions or hundreds of millions of clock cycles, that's still like a fraction of a second, right? So that's fine. We don't need it to be very fast, so we can use one of the Neos, you can kind of dial down its performance and make it smaller. So we use a very small version of Neos. It only uses a few hundred lookup tables. So it's pretty small. So we actually embed one of these. If we have multiple DDR interfaces, so you might have a big design that has 6 DDR interfaces, they each get their own Neos. So this would be an example where the fact that we can stick these soft processors wherever we want is beneficial because it's just stuck right in the IP. You want more DDR interfaces, you get more soft processors. If we use the hard processor on the chip for this, first, on most of the Altera chips, there's only 2 of them, so we actually might run out. They might be in the wrong spot, and it might be noticeable, right, that we stole the hard processor. So it's a good example for making a cheap soft processor. Then we connect over a coprocessor bus. Okay, so the time we did this, we used Avalon. Axie is becoming increasingly dominant, but doesn't really matter. So we have this on-chip RAM. So there's some RAM that we can use, like block RAM. We have a write coprocessor. And we have a read coprocessor. Okay, so each of these is like basically direct streaming hardware. They present a few registers that you can write to control them, and that they can capture, their status into. So the processor can query what I sent you a command. I told you to do the following. What happened, right? So the processor is just reading and writing these registers over the bus. And these coprocessors can do anything they want, so they actually hook straight to the DDR. They hook straight to the device I/O pins and to the DDR3 chip. And they're fast, right? So they can run. They can run at the full speed, right? 64-bit wide, 1.6 gigahertz. So the coprocessors. Let me go and erase this. Okay, so coprocessors are fast. They could do 12.8 gigabytes per second data transfers, which a soft processor can't even come close to, right? So you could not directly wire up a soft processor or even a hard processor to the device pins and have it do things at these kinds of speeds. And to calibrate, you have to do things at these kinds of speeds. Like you have to send full speed writes and reads. And the way DDR works is these things actually happen in bursts. So it's not actually just one data word. You have to send it a sequence of data words. They go to a sequence of memory addresses, and you have to read a sequence back, and you have to see how it all went. So it has to be fast. The CPU just does setup. Okay, so the CPU sets up the tests by writing to registers in those coprocessors. It analyzes the pass-fail. So the coprocessor just captures, you say write the following 8 words to this address. Okay, read from this address. Okay, send me what you got. Right? And now the processor can figure out what does that mean. So it analyzes pass-fail by looking at the data that came back. It can change the configuration. So it basically can write to registers to say things, well, adjust the delay of this signal by this much, adjust the signal of that delay by that much, change the PLL settings. That can actually start moving around some clocks that also affect where these strobes are, etc. Okay, so change the delay settings. Try the next thing, etc. Okay, so it's pretty complicated. Okay, this is an one of the reasons I use this example is it's a good example of where, like how you can leverage different compute models. Part of this belongs in streaming hardware, part belongs in a soft processor, in my opinion. Also, we have an alternative design. So DDR was a big problem for Altera for many years. It may still be a bit of a problem because I thought that I thought I made this pretty good, and then I came here and saw my grad students still struggling with getting DDR going, and I was like, oh, I thought I made it way better. Okay, but it was worse before I tried. Okay, so we had a different solution before this. And that solution was all hardware. Okay, so the earlier design team was in the UK, and they didn't use a soft processor. They used like a completely hardware solution. So it was essentially like a finite state machine with data path. Okay, so an alternative compute model. How big do you think this? Okay, and the calibration algorithm also was not fast enough. Okay, so they couldn't get to the highest speed DDR standards, and new standards kept coming out. So there was a problem with trying to keep up. It was difficult to modify an all hardware decision with like a state machine controlling a data path. And the calibration algorithm still wasn't good enough. Okay, couldn't get to the highest speeds. How big do you think this was in terms of Verilog lines of code? Any idea, or you got a different question? You can ask your question if you want. So.
Like the coprocessor?
Yeah.
Would that be like hardened logic or?
Most of this is not hardened. Okay, there are little bits that are hardened. So right at the IOs, and as you go generation by generation, more of this gets hardened. Okay, so one of the reasons DDR3 was really interesting is that we didn't have that much hardened circuitry. The latest FPGAs, as this matures, and you see most designs want this, you take this same logic and you harden it. So more of it's hardened in the latest chips. In these chips, basically near the IOs, you have some hardened circuitry. Okay, so like the last double the clock rate circuitry is hardened. And there's also what are called delay chains. Like programmable delay chains are basically a chain of inverters, okay, with muxes that you can control with SRAM bits. Okay, let's see if I do this properly. So that's like a programmable delay chain. Okay, and there's SRAM bits here. And this is your input, and this is your output. Okay, so I send a signal in here. The delay of each of these inverters maybe is 40 picoseconds. By programming a different number of inverters, I can pull the signal out. Let's say these are buffers. Say they're pairs of inverters. Okay, so there's no inversions. And they're pretty fast, so maybe there's like 50 picoseconds per pair of inverters. By programming different values in here, I can basically shift my delays in 50 picosecond increments. So FPGA IOs have these in various places. Because to do the fine sort of delay adjustments, this is what you need. So you have that, but then most of the logic driving this, the buffers, et cetera, are in soft logic. Does that make sense? If you took the latest Altera chip, probably like more of it will be in hard logic, because as you come up with good solutions and people use them a lot, you harden more of them. Okay, so it's a good question. Okay, so if you wrote this all in Verilog, you're making a finite state machine that's controlling a data path. How much Verilog do you have to write? Thousands. Okay, 1,000?
Although even more, like around 100,000.
Okay, so you say 100,000 lines. Whoa, you could write a lot of Verilog. Okay, anybody else want to take a crack at this? That's a lot of Verilog. What do you think?
I'm going to guess 50,000.
50,000. Okay, so actually this team in the UK looks pretty good, okay? Because I was amazed by this. It's 20,000 lines of Verilog, okay? The vast majority of which was in one big state machine, okay? So that is a lot of Verilog. You guys are like, no way. I mean, what are your labs like here? What are we doing to you? Okay, so yeah, it wasn't this much, but 20,000 was a lot. Pretty hard to maintain. It also actually starts getting slow. The state machine is so complicated and has loops in it. It was also hard to make the state machine fast enough, hard to modify, and started taking a significant amount of area. So basically this whole thing, not only was it harder to modify and make complicated algorithms, it was also larger than the whole microprocessor. So this would be an example of, as you get into complicated control flow, there comes a point at which you should stop making finite state machines, and processors actually are a really good way to do control flow. Okay, so that's one example where like these augmented soft processors can be very useful. Another example, I won't go into this one in as much detail. So FPGAs are used a lot in packet processing. So you've got these very high-speed switches that Cisco and other companies sell that are switching packets. And most packets are kind of boring, right? Like they have a header that makes sense, it's correct, it says go here, and you got to switch those at line rate. You know, like 100 gig, 400 gig, they got to be done very fast. That's all done in hardware, okay? So hardware looks at the packet, does all the lookups in a big spatial pipeline, and makes it run fast enough. But you do get some unusual ones. You'll get some packets that actually have an error. You'll get some packets that actually are saying, I need you to reconfigure some routes. They're much more rare, but what you do with them is more complicated. So that's called the slow path in packet processing. So the unusual packets. So most packets in FPGA systems go through the fast path. Okay, so they just need to be switched to their destination. So they go all hardware. Okay, so they're never touched by any kind of software, and it's the fast path. But you do get these exceptional ones. Okay, so there's some management packets. which means like I'm updating my routing tables. You know, other exceptional packets. And those ones, it's kind of wasteful, given that most of our packets are not going to go through it, to build like them into our spatial pipeline, right? Where it'll be underutilized, but it'll still take a lot of area. So this is the slow path, and we'd like to send it to software. So often this is sent to software. This is another use case for hard processors. In things like 400G and above networking, even the slow path can be pretty fast, right? Even if only 1% of packets go through it, it can still be a fair amount of processing. So this is still often too fast for a soft processor. So this is basically one of the arguments for a hard microprocessor. Not the only argument, but it'd be a use case where having a faster microprocessor available is useful. Okay, so that's all I had to say about the augmented processors. I guess the last thing I'll mention is I guess we already talked about this a bit, but basically you can make a vector processor. So it's just a processor with SIMD. We kind of already talked about that you could do that and use a finite state machine to control it, or you can use instruction logic to control it. All right, well, let me write that down for completeness. Okay, so you can make a vector microprocessor, which is just a microprocessor with SIMD. Okay, and nowadays, the hard processors in an FPGA would usually have that. The soft processor, you could decide whether you wanted to use it or not. If you're only using it for control paths, it's not really very useful. If you're going to do some data processing with it, then it might be useful. Okay, so I'm almost out of compute models. Probably be happy to know. Okay, so the next one is a little more bespoke. Okay, cellular automata. Okay, so what does that mean? Okay, so this is a compute model that's very useful when you have computations that are on a grid or a lattice. Okay, so this is particularly useful for physics. Okay, so 2D or 3D partial differential equations can be attacked with this compute model. Okay, so I'll show you an example. So erase this. Okay, so let's say we want to solve Maxwell's equations in some part of space. One way you can do that is with something called the finite difference time domain method, what that is when you learned calculus, you learned how to do differentiation. You take differentiation and you take it back to what they originally showed you to think of differentiation as, which is finite differences. So just differences between points that are close together. This is a method that you can actually use to solve complicated partial differential equations that you can't analytically solve, which is most of them. You basically make a grid of points and you turn the partial differential equation into like difference equations. Okay, so it's no longer infinitesimal differences, it's now small differences. And if you make a big lattice, like a whole bunch of points, you can model a pretty complicated geometry. And you can basically just walk through the geometry applying your difference equations in space and in time, and you can see how basically the physics of your problem evolves. Okay, and it basically works for any partial differential equation. So it's a pretty powerful technique. You're just taking the infinitely small differentials and you're turning them into small differences between points in a grid. Does that make sense? I'm going to take it as you. I'm not going to go too far into electromagnetics, so I'm going to take those blank stares as like you kind of believe me, okay? So this is a general way to solve physics problems. So if we take, for example, Maxwell's equations, right? So we have, this is the x-directed component of the magnetic field. I've got a y-directed component. So this is at a certain point in space, right? So I'd have a variable that represents what is the x-directed magnetic field right there. And then I have other variables that represent the y-directed magnetic or electric field here and the y-directed electric field there. And if you remember Maxwell's equations, you know that the change in these electric fields will produce the next magnetic field here, okay? So if I do this throughout space for all my electric and magnetic fields, I can actually model Maxwell's equations. And I can solve pretty much anything, right? Like what radiation is coming off an antenna, et cetera. So that's all kind of background. And basically, you can use this for all sorts of physics problems. Anything that can be described as partial differential equations. From a compute model perspective, the thing that is nice is you've got this grid. So you've got data distributed in space. That is the physics problem. And then the updates to this data are all local operations, right? Like the magnetic field at the next time step is a function of the electric field. Like both the magnetic field at the current time step and the electric fields around it, okay? And that just comes from Maxwell's equations. So basically my data is distributed and also the operators that will update it are also distributed. You're just taking small like differences of data around you to figure out what your new data is. Does that make sense? You don't really I'm not going to do any examples of the differential equations, just take my word for it, right? But that's how it always works. Okay, so we can think of the data and the operators all being distributed in space, all being at grid points. Okay, so this actually is kind of nice for spatial computation. We actually like when things are distributed. And here both our updates, our operators, and our data is distributed in space. So we can implement this in spatial hardware. Okay, so what's good about this if we map this to spatial hardware? Just like see if anybody's still awake, or yeah.
There's always like some sort of like pipeline going on because there's always inputs and outputs from the process that every part of the
Yeah. So my outputs are a function of my inputs, which are near me, right? So there's a very nice spatial pipeline. So the positive is, outputs are a function of inputs or my data nearby. So there's only local communication. Which is good in an FPGA, right? It's really good at local communication. You just wire things together. There's only local storage. I only need to look at the data near me. And I update right in place. Okay, so this is really fast. So you can get massive parallelism, really fast physics solvers. But you don't usually get positives without some negatives. So what's the negative of this? Yeah.
Really high utilization for this.
Yeah, so your negative is it can use a lot of hardware, okay? We're building we build like a little storage, a few registers to store each of these quantities throughout this grid. And we build like some subtractors and so on to do the updates. None of them are that big, but as the grid gets big, the design gets big, okay? And it may eventually exceed the size of our chip, okay? So negative is that we run out of hardware for big problems, for big grids. And especially in 3D, these grids can start getting big pretty fast, right? People care about the cases they really want to make fast. Not always, but usually are pretty big grids because they take a long time. And our challenge is that that can now start taking so much hardware if we just make a different compute unit for every one of these grid points that it just exceeds the size of our chip. So that's a problem. So there was a paper where they used this style of hardware to make an FPGA placement engine. So they could basically just decide by looking at the local neighborhood of where things were placed, what should I do next? It was super fast, but in order to place 2,000 LUTs, so solve a placement problem for a 2,000 LUT FPGA, it needed a 1 million LUT FPGA, okay? So there was a problem, right? It could make a really fast placement engine for a small FPGA as long as you had a really big FPGA to implement it. So that's kind of the problem of running out of hardware for these ones. So there's a variation on it, which is folded cellular automata. Okay, so what that is you say, well, the whole geometry, maybe it's a 200 by 200 by 200 grid. I can't implement that. It's too big. So I'll just implement a smaller part, maybe a 10 by 10 by 10 grid. I'll build all that storage. I'll build all those operators, like the units that can do the updates. And now that will fit on my FPGA. So you implement a part of the lattice or part of the space. And now what you have to do is you have to stream data through it. Okay, so it's only doing a part of the space, so it has to get new data in that represents a new part of the space and update it, and then get new data in and so on. Okay, so the positive of that is you can do any size problem. The negative of it is you've lost some of your performance, right? Like you're now streaming data through and sending it out to global storage. So you start winding up with some central storage bottleneck too. So you have a kind of a trade-off here. You can do bigger problems, but you've lost some of your performance. So you can have a memory bottleneck. It starts looking more like streaming at that point. So it's a lot like streaming at that point. Okay, so you're streaming data through, and it solves part of the lattice, and then you store that, and you stream more data through. It can still work well, and people do this, but it's not quite as efficient as, well, it isn't as efficient as if you could unroll the whole thing in hardware. Let's see. Okay, so the last couple of things I was going to say, let me just erase this, is Okay, so we already talked about multi-threading in the context of C-slow retiming, but basically you can apply to multi-threading to any style. Okay, so for spatial hardware, it's kind of C-slow retiming, but you can apply it in other ways. For example, microprocessors, most high-end microprocessors can run 2 threads in hardware, and they can basically switch between them. So when they basically can't find enough work to do on one thread, they basically can interleave instructions from another thread and keep their functional units going. So that's another kind of multi-threading that's employed in a processor data path for high-end processors. So it's a style that you can apply pretty much on top of anything. Sometimes it makes more sense than others. And then the last thing I'd say is you can combine all these. And we already went through a couple of examples of those, right? So when we talked about the DDR calibration, that was really combining a soft processor with some streaming hardware to make an augmented processor system. So that's pretty common. When you get to full systems, usually they are using a mix of compute styles, although there's often like a dominant one that they're using for most of the hardware. Let's see. And I guess the last thing I'd say, so the simpler models, like we started off with like this sort of a very simple model of like an inelastic pipeline, right? So you can't stop the computation, you can pipeline it with simple registers. So the simplest models tend to be very efficient. If you can map your computation to it, it's a good idea to do so, but they are more limited, so often they can't do everything you need, so then you have to mix in some of these other ones. But I think that's probably a good heuristic. If you think, first, what is a pretty limited but efficient compute model? Can that solve my problem or part of my problem? Start with it. So that was all I had to say about compute models. I was going to show you a few things about tools that help you implement those. Do you have any questions on any of that? Yeah, so go ahead. I'm going to start the projector while...
Just a very general question, because I think like you have a lot of like different languages, but I don't know to like put them sort of in an organized way that you can choose the best one as possible. Do you have any?
It's like, what is an organized way to choose the best compute model? Is that what you're asking? It's kind of like a bit of an art. So the truth is I don't have like I guess my most organized way would be start with the simplest ones. Like I said, like that inelastic pipeline sort of streaming. And if you don't need back pressure, and then just don't use it. If you have latency that you can't, and differences in throughput, then put back pressure where you need it and buffering where you need it. If you got a lot of control logic, then start thinking about a processor for that part of it. But I'd say this is more art than science. Like this is why, you know, the architect of a large hardware system usually makes a lot of money. And there's a reason, because he or she is not actually easy to replace. So I think it's difficult to distill down to like just always do this. Does that make sense? So let's see if I can make this wake up. Okay, let's see what it's doing here. Okay, let me turn off the lights. Okay, so I just have a few slides, so this won't be too long. Okay, so we already talked about cellular automata, but I can't make really beautiful pictures. This is a more, wow, okay, that was a good picture. Let's see if I can turn that back on. Okay, it's alive. Okay, so this is like a full grid for Maxwell's equations showing all the electric fields and all the magnetic fields in the various grid directions. So this is like a unit cell. You repeat this maybe 200 times in each direction, and you can model more interesting geometries like this. This is what's called a horn antenna. So you send in a waveguide with electromagnetic energy on one end, and radiation comes out the other side, okay? Not harmful radiation, right? So this is like cell phone radiation. So it's not believed to be harmful. One of the things people care a lot about this is like, where does the radiation go? You'd actually like to make a directional antenna. Maybe this is pointing, at my cottage, we have like an antenna pointing at a tower to get internet, okay? So you'd like that to be highly directional. You actually want it to just send data to the tower and receive data from the tower. This is showing the pattern of the radiation. So it's pretty directional. And this was simulated using this finite difference time domain method. So basically, there's a grid, and you've updated all the field equations, and at this spot back here where there's a waveguide, the fields are known, and that basically those fields propagate through the grid, and you figure out what happens at the end of the antenna. And you can do this for like any antenna geometry, so it's pretty powerful. But it has to step through the whole grid, and it has to do it for every time step, right? Because this only gradually evolves through time, so it actually takes a lot of compute. So it's a good case to accelerate. And there's at least one company that makes FPGA accelerators specifically for finite difference time domain, for like this exact problem where they want to make you boxes that run really fast. One of my friends from undergrad created a company called RTDS, which we have a bunch of their systems here in our power labs, and they do a similar thing where they use FPGAs to accelerate these kinds of physics calculations, but for power grids, okay? So they're able to do them so fast that they can hook their boxes into real power equipment. Like they can actually hook it into like a power system and have it pretend to be like a new generator, for example. And they can see, is this new generator going to work or not? But it has to be really fast. It has to keep up with the power grid because they're pretending to be a generator and you're seeing what happens. And the reason people buy their systems is whenever there's a major power outage in some country, like remember the east coast of North America, when its power all went out like 10 years ago, they then got a whole bunch of sales, right? Like basically whenever somebody takes out a big part of their power grid, they sell a lot of these boxes to simulate what will happen under various events or if you put in new power distribution things. In their case, they're solving circuit equations, so the grid points would be basically nodes in a big circuit, but it's a similar concept, right? You can map the operators and the data onto different pieces of spatial hardware. Okay, so we've been talking a lot about computation models. The reading that is due on Friday, is from the textbook, and it kind of draws this distinction of system architectures and compute models, which I didn't really draw. And it points out that the compute model that you choose also affects usually how you describe your system. So these are a few slides about that interaction. So yeah, mostly we've been talking about compute models in terms of how do you organize your hardware, what's efficient. But they also do affect how you might describe your system and implement it. So if you're doing general hardware, so just hardware that's got all sorts of things mixed together, you're not quite sure what it is, the hardware description languages are the most powerful thing. Often now, but not always. I mean, for high-end systems where the people need a lot of throughput, they usually write it in HDL. If they need to get something faster, they will often write it in high-level synthesis. Sometimes they'll write some blocks in HDL, some in high-level synthesis. So what's high-level synthesis? It goes from a language, usually it's C-like. There's no standard, but it's usually something that's C with some extra constructs. And the key distinction between HDL and high-level synthesis is you don't have clocks, right? And in HDL, you've decided where your clocks are. You know whether you pipelined or not, et cetera. In high-level synthesis, you don't know that anymore. You might give the tool hints, but it's up to it to decide where the clocks are. So that could be a productivity advantage, but it's usually come with a performance penalty so far. But there's lots of people working on that. Soft processors. So if you write a soft processor, usually you write in C, and if you need coprocessors, you usually develop those in HDL and hook them up with the Axi bus. Streaming data flow. So you can do that in HDL, and it's often done in HDL. But there are also some domain-specific higher-level synthesis tools. So these are ones that, they're targeted at only making streaming hardware, usually for a certain kind of system. And I'll talk about one of those. HDL is like the FPGA assembly code. But unlike assembly, people do write a lot of it directly. And even if you don't write it directly, if you used a higher-level synthesis tool, its output is HDL. So it's useful to be able to read that and understand what it's doing. Okay, so high-level synthesis. I'm not going to talk more about HDL because you're going to use HDL in the course, so you will know HDL. But high-level synthesis, again, the key thing that defines high-level synthesis is it's not timed. Okay, so you haven't said what gets done in every single clock. There are a lot of variations. Most of them are some variant of C with either extensions to the syntax or pragmas. So pragmas mean directives to the compiler. So it means that it will still compile in a compiler that doesn't understand the pragmas, but the pragmas give extra information for efficiency, et cetera, to a compiler that knows how to do high-level synthesis. Their output is Verilog or VHDL with clocks inserted. These tools are pretty popular. So both AMD and Intel and Microchip have high-level synthesis tools that are basically variations of C with pragmas, and they make a block of hardware that you can then integrate into your overall system. So that's one use of high-level synthesis. For this block, I'm going to use high-level synthesis. There's another use of high-level synthesis, which is to build an entire system. Okay, so both Intel and AMD have tools based on OpenCL, or OpenCL changed its name at some point to SYCL, so these are kind of the same thing. And what those ones do is they basically make the whole system, all the hardware, and they actually make the host code. So they assume that there's a CPU that is controlling the whole system. And the nice thing about these specifications is it's all kind of in one set of code, like both the code that will turn into the hardware accelerator and the host code that will set it up. It has proven difficult to get really good performance out of this. So I'd say this flow is probably losing some mind share to this one, where you just make IP blocks and integrate it into a design yourself. This one is sort of beautiful. It would make the whole thing, the whole system all in one standard way, but it's been hard to get kind of the highest performance out of it. So let me talk about another high-level synthesis tool. So who's ever heard of Simulink? Okay, so a few people. So actually quite a few. Maybe a bunch of you do DSP things. So I hadn't heard of Simulink before I went to Altera. Okay, so Simulink is a block diagram tool from MATLAB. And so signal processing engineers use it a lot to evaluate what's going to happen in some communication system or other signal processing system by hooking together block diagrams of various things, filters and up converters and down converters, et cetera, and see, what was my error rate, what was my signal to noise ratio, et cetera. So at least Xilinx and Altera have basically hooked into that ecosystem because a big part of their market is signal processing, so that engineers who use Simulink and are using it to figure out, is this system going to meet my signal to noise or bit error rate or whatever requirements, can generate hardware. So Xilinx has something called System Generator. Altera has something called DSP Builder. At a high level, they basically are very similar products. What they have is IP cores that are parameterized for the key signal processing blocks. So if you build your system just out of these blocks that they have IP cores for, when you're happy with your signal processing metrics, you can push a button and basically just generate all the HDL. Okay, so you didn't have to write any HDL, you just got a system that matches what you put in Simulink. And this is slides that I stole from Altera. And they basically say you just enter the design, you specify the target frequency, you push the button. So they're saying it's that easy. I'm not sure if it really is exactly that easy, but that'd be pretty easy, right? So, and it generates RTL. Okay, so I know the Intel DSP tool better because I knew the person who developed it. So again, its programming model is these block diagrams that are all describing streams of data. So it's a pretty natural fit to streaming for signal processing. The architecture that it generates is synchronous data flow. So it has data, it has valid bits on them. It doesn't use much back pressure, which is interesting. So it does use a little bit, but basically the tool tries to minimize how much buffering and back pressure it needs by essentially making the throughput of the downstream blocks high enough that they shouldn't back pressure. And that's done for efficiency. So the person who created this tool found that was better than basically more aggressively using back pressure signals. The data path automatically narrows and widens to deal with differences in rate. Okay, so if you have a decimation filter, the data path gets narrower. If you have an interpolation filter that basically produces a higher speed of data, the data path gets wider. So he did that instead of changing the clock frequency. So he made all his IP blocks try to run at the same frequency, and what would change is essentially the width of the data going in and out of them to match their data rates. So he'd send twice as much data per cycle, for example, if this was a part of the design that needed higher data rates. And then basically the tool aggressively repipelines. The nice thing about this tool is because it knows everything's feed forward, like it actually understands what each of these IP blocks is doing. So all the IP blocks they know how to pipeline themselves more deeply. So it can actually increase its pipeline depth. They'll retime it, and it basically wants to hit this clock frequency. And it hits a pretty high clock frequency. In a 40 nanometer FPGA for a big system that fills the whole chip, it'll hit 400 megahertz most of the time. So in like a really cutting edge FPGA, this would probably be more like 800 megahertz, which is pretty fast. In this case, there was an earlier version of this tool that actually did run the different operators at different frequencies. So it didn't do this trick of run everything at the same frequency and just widen it over the data path. And it didn't work as well. So this is another case where we actually have an apples to apples comparison where it was actually better to try to make everything run at the same frequency and just change the data path width. And it does use that technique that I talked about of multi-thread, taking an IP core that's really fast and your other IP cores can't keep up with it. It will actually time domain multiplex multiple streams through it. Okay, so it uses that trick as well of basically tagging data with a channel number to basically keep all the IP blocks as busy as it can. If you want to know more about it, chapter 8 of the optional textbook, Reconfigurable Computing, talks about Xilinx System Generator, which is basically exactly the same style of tool built by Xilinx. Okay, so a few other tools. Okay, so if you're building a software and a coprocessor, now your design style is a little different. You can write software code. You can build, if you need the soft processor to have some accelerators, you can build them yourself in HDL, or there's a library of ones that you can get from IP cores. You can integrate them with the processor by writing AXI buses in HDL. But because this is a pretty common thing to do, the major FPGA vendors all have system integration tools where you basically just drop down the blocks. And you say, I want these coprocessors to talk to this processor, and I want them all to use the AXI interface, and I want them to have these registers. And it'll automatically create all the buses. So you could do it all in HDL, but this will just do it for you. So it's easier. And for Intel, that's called Platform Designer. And for AMD or Xilinx, it's called Vivado IP Integrator. And AMD has a cool tool in Vitis, which they keep renaming, okay? But now it's called Vitis. And you can develop a C or C++ application, profile it to find hotspots. You mark the hotspot functions to be hardware accelerated, and high-level synthesis turns those hot functions into hardware, as long as they use kind of only a restricted subset of C and C++. It runs that hardware accelerator as a separate thread. So in your software, you can basically poll it or set locks to synchronize. And this is an example of the coprocessor design style. So it's actually building a coprocessor and it's connecting it with the AXI bus. So this is like a fast flow where you wrote software, you tagged some of the hotspots, they got turned into coprocessors, and you wound up with basically a processor plus a custom coprocessor, pretty quickly. There's an academic tool called LegUp, which is now part of Microchip, so it's both academic and commercial, which does something very similar. So those are interesting tools where you start completely from a software spec and kind of only build the hardware that you need in a pretty automated way to try to speed things up. Okay, so that's it. So basically there are a bunch of tools. You want to know how to write HDL as kind of the fundamental language of an FPGA or an ASIC. But depending on how you're describing your systems, there usually are some higher level tools that can help make you more productive. And with that, we'll end it for today. Okay, thanks.